Buck-boost power supplies were introduced initially to serve early AXE, stored processor-controlled telephone exchanges. Since their inception, a number of outages have occurred due to a lack of understanding and subsequent misoperation of this equipment. These outages, in most cases, have been severe, resulting in lost revenue and a large number of customers being affected. Let us now examine the buck-boost power supply system by first comparing it with alternative power conversion systems and then explaining its modes of operation in some detail. Telephone switching equipment can also be powered using rectifiers, batteries, and a DC distribution cubicle, depending on the installation. This is arranged as an integrated power suite, commonly called IPS. Buck-boost power supply systems are not configured or operated in the same manner as an integrated power suite. This is an extremely important point to remember. Let us first look at the integrated power suite. An IPS consists of a number of regulated rectifier units whose combined current output can supply the exchange peak DC load. One additional rectifier is provided to cater for redundancy in the event that one of the rectifiers is shut down due to maintenance activity or a fault condition. This arrangement is commonly referred to as N+1, where N equals the minimum number of rectifiers required to supply the exchange load, and 1 equals the redundant rectifier. If we look at a simplified single-line diagram for an IPS, the AC input supply is connected to the input of the rectifier. Usually this is a 415-volt, three-phase supply. AC is applied to thyristors or diodes, where the AC is converted or rectified to DC, and with the required circuitry provides a regulated DC output. The total DC output is connected to the load through the DC distribution cubicle, where the standby batteries are connected in parallel via knife switches to the load bus bar. The number of batteries provided depends on the battery reserve time designed for the site. The exchange can still function even if all rectifiers are shut down, as the entire standby battery is still connected to the load. This system is referred to as an online battery supply. There are other online battery power supplies that may be used. For example, using large switch mode rectifiers that are now available. These all have the common feature that the standby battery is connected across the output of the rectifiers and is fully available to the load, independent to the state of the rectifiers. But remember, the buck-boost power supply system is different. Now let's have a closer look. Individual power supply units can be found in two maximum load capacities. These are 500 or 1000 amps. The 500 amp power supply is contained in one cubicle only. The 1000 amp power supply consists of two cubicles side by side, where one cubicle is called the rectifier charger and the other DC regulator. An operational buck-boost power supply system may consist of a number of units of either capacity or a combination of both, as shown here. As with integrated power suites, buck-boost systems are provided on an N+1 basis, that is, with one unit available for redundancy. The input of each unit is supplied with a 415-volt three-phase supply. The regulated 48-volt nominal output is connected to a common load bus bar. What makes a buck-boost power supply different? Let's look at a simple line diagram of one unit. This diagram can normally be found on the inside door of each cubicle. A buck-boost power supply can be broken down into four basic areas. 1. An unregulated rectifier. This converts the incoming AC to DC and is essentially an unregulated rectifier operating at maximum efficiency. 2. A buck-boost regulator. Its input may be either from the unregulated rectifier or standby battery via controlling thyristors, and is capable of providing full output voltage regulation under a wide range of input conditions. This is a solid-state DC device, which includes an inverter, which may have to be manually reset as a result of extremes of input voltage. 3. A standby battery charger. The battery charger is regulated and dimensioned at 1/10 the size of the main unregulated rectifier. Its use is to float the standby battery under normal mains conditions and provide automatic boost charging following mains restoration. 4. Standby batteries. Each individual buck-boost power supply has its own dedicated standby battery associated with it, which usually consists of strings of 26 2-volt nominal cells. Let's look for a moment at a simple diagram of a complete system, and you can see how the standby batteries are configured. The way in which the standby batteries are configured is one of the major differences of the buck-boost system to online battery supplies. Because each buck-boost unit is associated with its own standby battery, that is isolated by means of the battery thyristors and regulator from the load bar, this system is known as an offline battery supply. Under conditions of AC mains supply failure, the DC regulator will continue without any interruption to supply the exchange with energy derived from the standby batteries. Under this mode of operation, the DC regulator automatically compensates for the falling battery voltage and maintains the exchange at a constant output voltage. However, if AC supply failure was extended, for example, by prolonged AC mains failure coupled to emergency standby failure, the buck-boost module will continue to operate for the duration of the battery reserve. Regulation will be lost at the point where the voltage of the battery falls to approximately 44 volts. Another smaller high discharge rate battery, called a smoothing battery, is connected across the complete system at the output, as can be seen on the diagram. This battery may consist of either flooded or valve-regulated type cells, and can be easily disconnected by means of the isolating link, or fuse if provided instead of the link. The smoothing battery is used to maintain a constant output DC voltage during the transition from mains to battery drive and vice versa. The size of this battery is not sufficient to supply the exchange load for any extended period. Let us stop here and revise the important points to remember about a buck-boost power supply. 1. It is part of an offline battery supply system. 2. Complete shutdown of a unit within a system will isolate that unit's standby battery, significantly reducing the combined battery reserve time. 3. Each unit has a nominal standby battery reserve time of 1 hour minimum. 4. Never shut down more than one unit at any time. For a variety of reasons, local operational staff are required from time to time to operate this plant. Extreme care should be exercised at all times to prevent misoperation, which could place the network at risk. Each buck-boost power supply has a comprehensive alarm display located at the top of each cubicle. For normal operation, 4 green indicators should be on. A red or orange indicator will show any abnormal conditions with the plant. Careful diagnosis of alarm indicators should be done before any operational procedure is attempted. There are 4 main operational procedures associated with a buck-boost power supply. A. Startup. B. Shutdown. C. Regulator reset. And D. AC isolation. To assist the operator, these 4 procedures are detailed on a set of cards located inside the door of each power supply. Let us now look at each procedure in turn, and the video will show the location of indicators, switches, and circuit breakers. If you have the procedure cards available, please follow them as we go through the various steps. The table shows which indicators and alarms are active at the end of each step. It should be stressed at this point that these power supply cubicles contain hazardous AC voltages, and therefore extreme care to avoid any accidental contact must be exercised by staff. Let us begin with D, AC isolation. Looking at the procedure card, if a single buck-boost power supply needs to be AC isolated, then all that is required is to switch off its AC input, and it is recommended that the isolation be carried out at the power supply rather than at an external AC distribution point. This ensures that the correct unit is isolated. It should be noted that it is not necessary to carry out a complete shutdown, and approximately 1 hour is the maximum time the unit can be run in this mode at full load, assuming the battery was in a fully charged condition to begin with. This action automatically switches the buck-boost power supply to battery input regulated. That is, the standby battery supplies the load via the buck-boost regulator. However, any period of AC isolation to more than one unit must be well within the standby battery reserve time, otherwise long-term battery operation will lead to total failure of the exchange load. Step 1. Check that all buck-boost power supplies are online, supplying current with only the 4 green indicators on. Now check that all the indicator lamps are functional by operating the lamp test push button before proceeding. Step 2. On the 500 amp buck-boost, switch off the main supply circuit breaker 1CB1, or with the 1000 amp buck-boost, switch off the main supply isolator 1SW1. Check that the buck-boost power supply automatically switches to battery input regulated. That is, the standby battery supplies the load via the buck-boost regulator. The battery charger is automatically inhibited during the battery operation. The charger current meter should display 0 current, and the charger volts meter should display a slow fall in battery voltage as the standby battery discharges. Warning: monitor the standby battery voltage on the charger volts meter and ensure that it does not fall below 44 volts. Otherwise, the regulator will eventually fail to supply output current. Step 3. When AC isolation is no longer required, on the 500 amp buck-boost, switch on the main supply circuit breaker 1CB1. On the 1000 amp buck-boost, switch on the main supply isolator 1SW1. There will be a time delay of approximately 35 seconds before the buck-boost power supply switches to mains input regulated. The charger should automatically restore at this point. Check that the buck-boost power supply is load sharing with the others and only the 4 green indicators are on. Now to C, the regulator reset procedure, which is carried out if the buck-boost inverter has failed. The buck-boost regulator will continue to supply output current in the unregulated mode until the inverter is reset. A large main surge, or sag, is one of the most common causes of buck-boost output regulation failure. Step 1. Check that along with the other alarms in the table, A, the mains input regulated indicator is on, indicating that the regulator failed on extra high voltage, or that B, the battery input regulated indicator is on, indicating that the regulator failed on extra low voltage. Step 2. Operate the output EHV/ELV alarm reset push button PB1, which is located on card 2M15, to reset the output voltage high-low alarm. For extra low voltage reset, wait until the buck-boost power supply switches to mains input regulated. This may take about 35 seconds. Warning: If the buck boost power supply does not switch back to mains input regulated, then it may mean the main supply is not normal. Specialist assistance must now be sought before proceeding any further. Step 3. Switch off the DC output isolator 2SW2. The buck boost power supply must be switched offline in order to reset the inverter. Step 4. Hold in the inverter reset push button 2PB1 or 2PB2 depending on the model for about 3 seconds. The inverter should reset and the output voltmeter should display an output voltage slightly higher than 49.5 volts. Step 5. Switch on the DC output isolator 2SW2. The buck boost power supply should now supply current at the normal output voltage of 49.5 volts. Check that it is load sharing with the other buck boost power supplies and only the 4 green indicators are on. The next procedure that may have to be carried out is on card B, shutdown of a unit. This procedure is carried out only if there is a failure of any component within the buck boost power supply or for general maintenance purposes. You must ensure that the other buck boost units are still operating normally and are capable of supplying the exchange load before beginning. As this will isolate part of the standby battery, only one unit is to be shut down at any one time. This is the most dangerous procedure in relation to placing the exchange at risk. Electricians may have a requirement to work on the input AC power circuits, but it is not necessary to shut the complete unit down for this purpose. In this case, the AC isolation procedure should be carried out. Now to the shutdown procedure in detail. If you look at your procedure card, you will find a warning. Shut down one buck boost power supply only. Shutdown of more than one buck boost power supply will lead to total failure of the exchange load. You have been warned. Step 1. Check that all buck boost power supplies are online with only the 4 green indicators on. Now check that all indicator lamps are functional by operating the lamp test push button before proceeding. Step 2. Switch off the battery isolator 2SW1. Warning. The standby battery is now totally isolated from the buck boost regulator and the exchange load. Step 3. Switch off the charger AC supply circuit breaker 1CB2. The charger current meter should display 0 output current. Step 4. Switch off the charger battery isolator 1CB3. The charger voltmeter should display 0 output voltage. Step 5. On the 500 amp buck boost, switch off the main supply circuit breaker 1CB1, or on the 1000 amp buck boost, switch off the main supply isolator 1SW1. Warning. Check that the other buck boost power supplies have only the 4 green indicators on and are able to support the total exchange load. If not, complete step 6 and then restart using startup procedure A. Step 6. Switch off the DC output isolator 2SW2. The output voltmeter should display a slow fall in output voltage while the output filter capacitors discharge. It is important to note that all indicators and alarms will disappear once the capacitors are completely discharged. Ensure that this unit is put back online as quickly as possible, as it only takes one of the other units to go faulty and your exchange is at risk. Finally, let us look at the 4th and last procedure, A, startup. This is carried out when a buck boost power supply is to be powered up after a complete shutdown of the unit. The power supply cannot be started unless the input mains AC supply is available on each of the supply phases and at normal voltage levels. Step 1. Check that the control AC circuit breaker 1CB4, if fitted, is on, and the emergency rectifier operation switch 1SW4 is off. On the 500 amp buck boost, switch on the main supply circuit breaker 1CB1, or with the 1000 amp buck boost, check that the input contactor control 1CB1, which is fitted on late models, is on. Switch on the main supply isolator 1SW1. The output voltmeter should display a slow rise of output voltage while the output filter capacitors charge up. Wait until the buck boost inverter has switched from battery input regulated to mains input regulated. Now check that all indicator lamps are functional by operating the lamp test push button before proceeding. Step 2. Hold in both the output EHV-ELV alarm reset push button PB1, located on the EHV-ELV alarm card 2M15, and the inverter reset push button 2PB1 or 2PB2, depending on the model, for about 3 seconds. The inverter should reset and the output voltmeter should display an output voltage slightly higher than 49.5 volts. Step 3. Switch on the charger battery isolator 1CB3. The charger voltmeter should display the standby battery open circuit voltage of slightly less than 57.2 volts. Step 4. Switch on the charger AC supply circuit breaker 1CB2. The charger voltmeter should display a rise in output voltage, while the charger current meter may display maximum current. This is known as current limiting. On reaching 60 volts, the charger should reset to normal float voltage of 57.2 volts. Step 5. Switch on the battery isolator 2SW1. Step 6. Switch on the DC output isolator 2SW2. The buck boost power supply should now supply current at the normal output voltage of 49.5 volts. Check that it is load sharing with the other buck boost power supplies and only the 4 green indicators are on. This video should assist you to know your buck boost by gaining a better understanding of its method of operation and so become a more confident operator when next you have to work on this equipment. However, if you have any doubts, do not hesitate to seek help and consult with the regional telepower experts in your state or national telepower support.